Hello and welcome to this presentation. I'm Marcin Bosk and I'm a PhD student at the Chair of Connected Mobility at the Technical University of Munich. Today I will show you our work on the applicability of fifth generation mobile networks quality of service mechanisms for achieving quality of experience aware network resource allocation. Before we dive into the topic, first a quick overview of what we will be talking about today. First of all, we'll go over some motivation as to why we actually need quality of experience aware networking. Then we will describe the environment in which we evaluate those 5G quality of service mechanisms for quality of experience networking. We'll follow that with some evaluation of those mechanisms and conclude with a summary and some remarks. Why do we actually need the quality of experience aware networking? Well, the applications in today's networks are very heterogeneous in terms of their requirements placed upon the network. We can have, for example, voice over IP, which requires low latency, and video on demand streaming, which requires high bandwidth from the network. We can also have other applications, of course. The resources in those networks are split fairly between those applications and their flows, as you can see denoted by the dashed line here. That means that sometimes, because the applications are competing for those resources, their requirements may not be fulfilled. And this may lead to some degradation of user experience for some applications. In this case, VoIP might not be able to get the delay it requires, but our applications might be perfectly fine with the resources they are receiving from the network. There are, of course, solutions to this problem. The first and one of the more straightforward ones is the over-provisioning of network resources. But of course, this is not always feasible and sometimes impossible. And on top of that, it is expensive and inefficient use of the available resources. Other mechanisms include quality of service mechanisms that we may be able to use in a quality of experience aware manner. And this is what we will be taking a look at today in this presentation. Let's start with what quality of service mechanisms are actually available in 5G that we could use for the QoE-Aware resource allocation. The first of those mechanisms is QoS flows, which will be denoted on the graphic using this highlight that just appeared. The QoS flows allow us to set on a per flow basis QoS guarantees. What we will be looking at in this work is the guaranteed bitrate and the maximum bitrate, with guaranteed meaning that the application or flow is guaranteed to get a certain bitrate, and the maximum bitrate means that the flow can get up to this maximum bitrate in case there are resources available, free resources available in the network. This approach is very fine-grained and thus also highly complex. So the other approach that we'll be taking a look at is network slicing, which basically means that groups of flows may have dedicated virtual networks assigned to them, denoted here by the different colors of clouds. And then, of course, the flows are routed through their respective slice. Those slices can be strongly or weakly isolated against each other. That means we can have hard slice isolation or soft slice isolation between them. And this approach, of course, is more coarse-grained as we are having the quality of service guarantees aggregated between the flows. So this is not per flow, but per group of flows. This leads us, of course, to a few questions. Initially, how well are actually those both concepts suited with respect to efficiency when talking about network resource utilization, and also how well are they suited to guaranteeing a certain quality of experience level for different application types? But then also what this brings us to is how do we actually configure the quality of service flows considering using user experience, and how do we isolate traffic corresponding to those different applications, for example, when talking about network slicing. But then in order to even configure both of the approaches, how do we quantify user experience into the quality of service parameters that we need to configure the network? And finally, can we also combine both of those concepts so to increase the network utilization efficiency and also possibly the quality of experience? To answer those questions, we have defined an experimental setup using the Omnet++ simulator together with INET framework and a custom in-house built hierarchical token bucket queuing module. We of course make some simplifications. First, we focus only on the 5G core network, that is a simplified environment without the radio scheduler, and we are realizing the per flow quality of service guarantees using the hierarchical token bucket module. In all of our experiments, we are using 5 application types, that is voice over IP, secure shell, file download, video on demand, and live video streaming. And in each experiment, we just have one application per client. In terms of network slicing, we are looking at 2 approaches to realizing it. The first one includes perfect isolation, so hard slice isolation, and that is that one slice is its own separate and independent network. And also we are considering the shared environment effects where one slice is a rate limited grouping of clients and flows. To configure the QoS flows and also network slices, we need to quantify the application requirements. And we do that using something called utility functions, which map the delay and bandwidth requirements of the application to the obtainable QoE, or in this case, the mean opinion score, which is given on a scale 1 to 5, with 1 being unacceptable and 5 being good quality, a good experience. And those values are obtained, those utility functions are obtained using simulations where we just have one client in the network and we are varying the network parameters. Here on the right, you can see examples of those utility functions presented as heat maps. And based on those utility functions, we are able to classify our 5 applications into 2 main categories. We have delay-sensitive applications and bandwidth-hungry applications, with an example of delay-sensitive applications being VoIP, for which you can see the utility function here on the top right. As you can see, above a certain bitrate, the available bandwidth doesn't matter anymore, and the user experience is only dependent on the delay, on the network delay. Then we also have bandwidth-hungry applications, for example, the video on demand streaming and file download. And there is also a special case for the live video streaming application, which is both bandwidth hungry and delay sensitive. And as you can see on the example for the live video applications utility functions here on the bottom, we can see that the user experience depends on both the available bandwidth as well as the delay. Now that we know how to configure the QoS flows and the network slices, we also need to be able to enforce those configurations. And what we are doing in this work is we are using the hierarchical token bucket implementation, which is a classful token bucket algorithm to enforce this. HCB allows us to level rate control for all of its classes. That is, we can control the guaranteed bitrate and the maximum bitrate for each of the class. And it realizes this in a hierarchy that you can see here on an example of which you can see here on the right, where we have 3 class types. We have root, which more or less corresponds to the available network resources. We have inner nodes, which then group the leaf nodes on the bottom, and only the leaf nodes have Q attached to them. And then, of course, we can configure the guaranteed bitrates and the maximum bitrates for each of the classes individually. And what we are doing with our work is we are mapping the leaf classes into QoS flows. Thanks to our implementation, we are able to assign the guarantees to each flow that we have in the network. And also we are abstracting the inner classes as network slices, which emulates, in this case, soft slice isolation, because we still may have effects between those classes here. For hard slice isolation, what we do is we run each slice in its own separate simulation with its own separate dedicated network resources that cannot be influenced by other classes. And of note here as well is that we are not proposing the hierarchical token bucket as the solution for any network deployments. We are merely using it as a tool that allows us to emulate the QoS flows and network slices. That baseline information behind us, we can go to the evaluation and start with what scenarios we are actually investigating here. Through the evaluation, this table on the right here will be following us, in which you can see an overview of the scenarios with their name, whether we used admission control or not. We are admitting clients into each scenario, whether we were using QoS guarantees or whether we are using tuned QoS guarantees that with which we want to exploit the multiplexing gain that we have using slicing. And then also whether we were using the hard slice isolation or soft slice isolation in case we are using, of course, network slicing. And to start with, we have two baseline scenarios, which represent the best effort case. In the first one, all clients are admitted. In the second one, we admit the same number of clients as if we were giving the quality of service guarantees. However, in both scenarios, we are not giving any QoS guarantees. That means we don't apply QoS flows or network slicing in this case. We follow that with QoS guarantees scenarios, where we are guaranteeing bandwidth for each flow individually. So we're using QoS flows. And we do that in order, and we want to achieve with that the quality of experience of 3.5. which is somewhat an arbitrary number, but it's chosen to be quite an acceptable value that's not too high and not too low. And we are defining those guarantees or which bandwidth we need to guarantee based on the utility functions that I introduced earlier, with the value that the utility functions give us being the guaranteed bitrate. And then we are defining the maximum bitrate as a percentage multiplier of the guaranteed bitrate. In here, we have three scenarios. The first one uses just QoS flows, so per flow guarantees with the settings as I just described. And the second, the latter two scenarios use the QoS flows as well as network slicing, ones with hard slice isolation and also then with soft slice isolation. We follow those scenarios with tuned QoS guarantees scenarios where we try to fine-tune the quality of service guarantees so that we can consider the multiplexing gain. And we also do that in three scenarios. The first one where we just use QoS flows, and the latter two where we also use slicing, ones with hard slice isolation and the other time with soft slice isolation. I said we want to fine-tune the QoS guarantees. What that means is, first, to understand this, we can consider a simple scenario where we just are using the QoS flows. And we are, what we observe is that those flows can borrow, but they can borrow from any other flow that's available in the network. So this means that application 1 can technically borrow bandwidth if there is an excess from application 2 while still being guaranteed their guaranteed bitrate. But what we actually want to do is that, for example, the delay sensitive and bandwidth hungry flows do not interfere with one another. And to do that, we try to combine the QoS flows with network slicing. That is, we are having one network slice per application type. And this implies that we disallow borrowing between those two applications. Then what we do is we can account for the application specific requirements, because the applications will be able only to borrow between the flow of the same application with the same behavior. What this means is we can make use of the intra-slice multiplexing gain more easily here. As an example, If we consider a voice over IP application, we have silence periods during a VoIP call. Someone is talking for a moment, then they are silent. So we are using the assigned bitrate only roughly 50% of the time. And what this allows us to do is lower the guarantees for those applications while still allowing the borrowing. And in turn, we can possibly lower the client rejection rate, reduce the complexity of the radio scheduler, or increase the network efficiency. And to do so in this work, we have run a parameter study where we have taken the value for each application that the utility function gave us, and then tried to reduce the guaranteed bitrate based on the original value. And also based on the original value, we then tried to encourage borrowing, so to exploit the resources better, the available resources better, and also keep the quality of experience guarantees as we set them at the 3.5 value. With that, we can come over to how we are admitting clients to our scenarios. The admission is done before each experiment, so that when the experiment starts, our clients are already in the network. And in each experiment, we have 150 clients incoming, each client having a certain probability of being of a certain application type or using certain applications. So for example, there is a 40% chance that an incoming client is a VOD client, 20% that it uses live video streaming, etc. Based on those values, we are also dimensioning the slices, and the slices are dimensioned once for all experiments. What this means is that in each experiment, we are using exactly the same slicing resource allocation. How we dimension the slices is we are using the client distribution and also the optimal bandwidth guarantees that we obtain based on the utility functions to determine that, for example, the video on demand slice should be getting 48 megabits per second of allocated bandwidth, the live video streaming slice should be getting 39 megabits per second, etc. And this is all out of 100 megabits per second that are available in total in the system. With the client distribution and the resource allocation for slices, we come up with the following numbers of admitted clients into each scenario. You can consider the BE1 scenario, the best effort 1 scenario, numbers also as the numbers of clients that are incoming into the system each time. Since we are using random distribution and the same seed for each client admission round, that means that the order of the incoming clients is the same in each scenario. I'm not going to go into too much detail here. We'll all touch upon it when we are talking about the quality of experience results here for all scenarios. So again, as I've said here, we have the table that's following us with the overview of the scenarios. And in terms of the flows, what we can see here is, first of all, that on the y-axis, we have the average mean opinion score. This is the experience that we observe in the system for each application type and also in total in the system, with the dashed line here showing the 3.5 that we are aiming to guarantee for all of the users. On the x-axis, we can see the number of admitted clients in each scenario. And also in those boxes here with the percentages, we can see the maximum bitrate multiplier that was used to determine the maximum bitrate based on the guaranteed bitrate in the non-tuned quality of service guarantee scenarios. What is also important here in this, each vertical box represents one scenario or one sub-scenario. And here on the left, we have the 2 best effort scenarios. Then we have the 3 scenarios with individual sub-scenarios for where we're using untuned QoS guarantees, ones just with QoS flows and then also with network slicing. And then here on the right, we have the scenarios where we fine-tuned the QoS guarantees and run experiments once without slicing and then with hard slice isolation and soft slice isolation. The first thing that we can see in this plot is that the increase in the maximum bitrate multiplier improves the quality of experience up to a certain point and up to a certain multiplier. What we can also see is that fine-tuning those QoS guarantees allows us to admit more clients into the network, reducing the rejection rate, while we are able to keep the same quality of experience for all of the clients. And in some cases, in case of some applications, like for example, the file download or live video, we're even able to slightly improve their quality of experience. The biggest improvement that we see from slicing comes for the live video application. And what we also observe is that the applications that have low bandwidth requirements, such as voice over IP and secure shell, usually obtain a high quality of experience. Continuing, what we also take a look at is system load. We want to optimize the network in such a way that we can also fully utilize it. So we have, to present those results, we have a similar plot as for the quality of experience. Just on the y-axis here, we can see the average system utilization if we consider the black dots, or we can see the average slice utilization if we consider the colorful dots, and in case network slicing was used in one of the experiments. The first thing we observe in this plot is that, again, the increase in maximum bitrate multiplier also improves the overall system utilization in all scenarios. And it also generally improves the slice utilization, most notably for the live video streaming application, but also for the video on demand application and the file download application. What we also notice here is that the network slicing generally decreases the overall network utilization, and that tuned quality of service guarantees improve the slice utilization, especially for the voice over IP and the secure shell applications. So what we have done in this work is we've investigated two of the fifth generation mobile networks quality of service mechanisms and investigated their feasibility for quality of experience aware network resource control. That is, we taken a look at the QoS flows and also at network slicing. And then we also combined those two mechanisms and tried to fine-tune the guarantees in order to better exploit the multiplexing gain that slicing brings us when grouping traffic of similar applications together. And with that, we can obtain more efficient usage of network resources while reducing the rejection rate and preserving comparable quality of experience levels between the scenarios. With that, I would like to especially thank Martin de Vera, the author of Linux Hierarchical Token Bucket implementation, for his help and support while we were implementing the HTTP module for Omnet++. I would also like to thank my co-authors for their help. And thank you all for attention. In case there are any questions, feel free to reach out either to myself or my co-author, Maria. And in case you are interested in some further reading, here are some references that I can recommend. Thank you again.